Um, yeah, so thanks very much for coming. This is so fun to have finally sort of wrapped up this course. So welcome to, I think the last time that we are connecting in the context of this course. Of course, it doesn't have to be the last time that we meet. Let me just see if I can get the video going. Right. So yeah, I guess yeah, it's been a really fun 12 weeks. I think let me just begin by taking a question in the chat, which was about being keeping the Discord community active and sort of continuing that after the course is over. And we certainly plan to keep the community active in the sense that there are no plans of closing it down or archiving it. I think for people who feel like they've outgrown the community and it's not relevant to them anymore, perhaps could leave the community. I guess that's not difficult to do on Discord, and they could come back whenever they feel like joining again. So I don't really see a need to necessarily close it down. I don't think that's required. So it'll definitely be around. In terms of how much everyone will continue to be active, this will depend. So I think we did discuss rerunning the course. I believe the course will happen again in the January semester. So I expect that we will end up using the same Discord forum in the next run as well. And I think all of you are welcome to continue discussing. Maybe, ideally, it'll be great if you could help out the new joinees. If some of you are taking it again, hopefully, informed sort of approach to the course. And yeah, it'll be new assignments and hopefully a little more structured than this time, because to be honest, I think I was I also didn't know exactly what to expect in terms of the audience. So I think your feedback has been very helpful in shaping the courses, for which I'm grateful. But what happened as a result of that is I think I started falling a little behind in the content because I started tweaking it based on, what I was hearing. So my plan is to maybe take on some of the things that are missing in the course right now, the things that I'd originally planned to do. So hopefully I'll get around to shooting some extra videos in December, and I'll put those in as optional sections that you can pursue, if you're interested. So in fact, in dynamic programming, I definitely wanted to do a lot more. And in fact, there are videos that are done actually right now, but I didn't want to release them because it's afraid of maybe causing overwhelm. And I just wanted to do an introduction to the technique and leave it at that. But if you come back to the course next time, then I think you will see at least 4 or 5, 3 or 4 more examples at least. One of them is from actually a core jam finals. It was a lot of fun to shoot. So I hope you enjoy that as much as I did. So yeah, I guess, so yeah, I do hope that, the Discord community will stay alive. There may be a quiet period from now to January or so, but I plan to be around. So please feel free to continue using it. Now coming to the main topic of this discussion, which is the exam. I think, I assume most of you are planning to write the exam this weekend. Okay, what is the pattern of the exam? Certainly there are no coding questions. Okay, so there's nothing that will require you to write a program, and there's no separate exam based on like on CodeChef or any other platform. We may invite you all to a CodeChef contest later once all this is over, but that'll be informal. It'll have nothing to do with the, it will have nothing to do with the grading process. Okay, so no coding, that is for sure. But that doesn't mean you sort of forget about coding altogether, because you may still be asked to either read code or at least think about certain algorithmic approaches and analyze them. And you may be asked to work out small examples, but they will be small enough that you can either do them by hand, or if you see a big number, then understand that it's some pattern that you can, like, everything should be doable with a calculator. So if you see that you have to calculate something for like some large values of the input, that means that there is some underlying hidden pattern and you have to discover that pattern and apply it. Okay, so I guess, yeah, so that's one tip. Other than that, yeah, the answers are either numerical or MCQ or MSQ, meaning it's not automatic that all questions have exactly one correct answer. So please don't assume that. But usually, from the way the question is written itself, it'll be clear as to whether there's one or more correct answers. Okay. Um, Okay, so fine. Will the question paper be tougher than the weekly assignments, or will it be one level below or more? Because you felt that some of the assignment questions were tougher than they usually used to be, meaning they got tougher over time. I'm just trying to understand, or are they tougher like within an assignment as you go from 1 to 10? You find that some questions within an assignment are tougher than the others. Just trying to understand how you feel about the assignment questions. Okay, so you're saying within a week you found it. Okay, DP questions were probably a bit difficult because maybe you didn't have enough examples to go with. I think I should have included more simple examples in the videos. But I was hopeful that you will have a chance to just practice the philosophy of DP. Would you like to have like a quick recap of DP even right now, just to like get the hang of it? Because the final exam will have a few DP based questions, will have a few recurrences, but yeah, they're really more recurrences than you're having to worry about DP. Okay, so let me just take a vote. Would anybody like a quick recap of DP based concepts? We could even go through the assignment questions as well, a few of them. Okay. All right. Okay, let's do that. Other than that, I think some of the common questions that came up on Discord was like, do we have to remember a specific problem like reverse sort, or I don't know, island war, or any of the other specific problems we did? You don't have to do that. Okay. So if at all we have a specific problem which we are asking you to solve, we will describe the problem completely and then have you solve it. One thing about the exam is that there are like, so the first part is short answer questions, and the second part is like, there will be one question which will have a lot of setup and description, and then there'll be lots of small questions based on that. Okay, so the idea was that you have to read a lot, but you'll also be able to answer a lot of questions based on what you have read. So and it'll have multiple parts. So basically, I would say don't get intimidated by the length of the question. Like, don't, like, if I'm writing an exam and I see a question that is that long, I'll be like, just leave this, who will read so much? Okay. So don't do that, because the idea is to help you read it, and then it may look like there are many questions, not all of them may be easy, that is okay, but you'll be able to answer at least some of them just by, it's like a reading comprehension, like did you read and understand the question the way we expected you to, right? So you will have definitely some easy wins if you just have the patience to read the questions. Okay, so do that. And but you could focus more on the first half if you like, which is more like at the level of the normal weekly assignment questions. And now let me just see if I can help a little bit with the DP part of it. Is there any other topic apart from DP that you want to recap of? Should we do a recap from the top a little bit? Like, I don't know how much time you guys have. I can spend a little bit more time than an hour if required, if that helps. This is like full on last minute preparation, right? But if it's useful and if you're all around, then why not? Did you get the solutions to the DP assignments in the email or on the portal? Okay, no, it will vary a bit. Not every question is the same weightage, okay? But most questions have a similar weightage. I think it's for 100 marks total, and questions are like either 2 marks or 3 marks, something like that. As far as I know, there is no negative marking, but you'll have to check, okay? Please read carefully. Okay, should we go through Ford, Fulkerson, Kruskal, Prim, and other sorting algorithms? I think it's a good idea to know these things in terms of, see, we may not ask you like something very explicit about, like if you implement Kruskal's algorithm with this data structure, what is the running time? I don't think there are many questions like that. But like you should at least know that Kruskal and Prim's algorithms give you spanning trees, right? And because that is, there may be questions that reference that, right? So yeah, I mean, I think in general, I would say it's a good idea to have a sense of it. That's why I was thinking, should we do a recap of like, at least the main highlights? Okay, so let me do this thing first, right? Let's do, I think it was a good idea to ask about week 10, question 1. In fact, let's do as much as we can of the week 10, 11, 12 assignments. I don't know if like some people had questions about the week 12 assignment also, which was essentially, anybody got the week 12 answers correctly here? Could you raise your hand? Oh, great. Awesome. Very nice. So, oh, thank you so much. Yeah, DP videos are definitely coming up. I really enjoyed making them. So I hope they have come out well. Segment trees, yeah, I've not really, yeah, I keep thinking about, doing more topics in CP. There is so much that we left out. So, it was always difficult to choose what to pick, what to leave out and all that. But yeah, I mean, segment tree is definitely a popular thing that we completely did not cover. And there are a few other topics like that, so would love to do it. I might just start putting up videos on like YouTube randomly. So, and I'll let you guys know whenever I do that. Yeah. So cool. Let me try to share my screen so you can follow along as I'm writing. Yeah, okay. Let me talk about, so that was like something that I'd kind of assumed that you might have seen when you were doing knapsack and all that, but okay, I mean, in like previous algo courses. So fine, let me just turn off my video here. It's like I have limited bandwidth, so I don't know if the screen share and video will be supported simultaneously. So you can see like this notebook thing on my screen, right? You just give me a +1 in the chat. Yeah, okay. Great. Super. Yeah, so let's start with these week 10, 10, 11, 12 assignment questions kind of thing. I'm just trying to pull up the assignment and I'll go back to the screen share. Okay, so let us study this. Yeah, let's study these proposed recurrences a bit and try to figure it out. Does anybody want to do the matchsticks question? Or should we do the pseudo polynomial? 2, 3, 5. Okay, we'll do like 2, 3, 4, 5. Matchsticks, yes. Okay, fine. Let's do matchsticks. So there are 19 matchsticks and 2 players, and on your turn you can pick 1, 2, or 3 matchsticks, right? So the player who picks up the last match is the loser, and it is the first player's turn. Okay, so right now there are 19 matchsticks given. Let's do a simpler, like a smaller example, okay, which is always useful. So instead of 19 matches, so game is clear, right? There are 2 players. So let's say the blue player is player 1. And the red player is player 2. And the last person who picks up a match is the loser, right? Then you don't have a choice. Like if there's only 1 matchstick left, you don't have a choice. So then you lose the game. So let's see. So suppose, so the first player starts the game. Okay, so that's player 1. So suppose n is the number of matchsticks on the table. Okay. So what if n is 1? Is that a losing position or a winning position for the first player? So I will just say it is a winning position or a losing position from the point of view of the first player, okay? In the sense that we'll always think about this from the perspective of the first player, yeah? So if n is equal to 1 and there's only one matchstick on the table, then what can you say? The first player will win or lose? Yes, the first player will lose, okay? So this is a losing position for the first player. Let me use a different color for player 2, otherwise this is confusing. Purple is fine, okay. It's a bit weird, but it's fine. Okay, so what about n equals 2? If there are two matches and you are the first player, what will you do? It's winning, right? You can pick one or you can pick two, and it would be, I mean, players are always rational and intelligent about these things. So you'll not pick two and shoot yourself in the foot. You will pick one and give it to the other player to lose. Okay. So this is a win for sure. What about if there are three matches? Similar logic. Three matches is a win. So, okay, I'm just going to go ahead and write the three matches as a win because the first player can pick two matches, leave one match on the table, the first player to lose, right? Okay, what if there are four matches? This is also a win because you can pick three matches to leave one on the table. Okay, I guess it gets interesting with five because with five, you have three possible moves. You can pick one to go to four, you can pick two to go to three, or you can pick three to go to two, right? If you pick three matches out of five, you're left with two. Pick two, you're left with three. And if you pick one, you're left with four. So what can you say about five? These are the three possible options that the first player has. Are you sure? Because when I make my move and I give it to you, then you become the current player, right? So if I give you a winning position, right? If I give you a position that is winning for whoever starts the game from there, then I'm going to lose, right? And the point is that no matter what I do, right? All of these three options. So from five, I can go to four, three, or two. Whatever I do, I land up in a place where the other player can win, right? Is that making sense? Because this is the crux of the matter. After that, it's done. Cool. Right. So if you have this winning streak of three things coming together, then you lose. Okay. So from five, you lose. Then let's think about six. So the point is, can you subtract a certain number of matches which takes you to a winning position? So from six, I can try to go to five, right? Because from five, the other person is stuck. No matter what he does, he'll have to move to something that is winning for me. So for six, it'll go something like this. This is what player one will do. He'll push one match. And then five, I know, is losing for whoever starts from there. So no matter what the second player does, let's say the second player takes two matches, they leave me with three, which means that I will do two matches from there. Whatever the second player does, it doesn't matter. So I will pick one match. The second player could pick one, and then I will pick three. And then the second player loses. Or the second player could pick three. This we have already discussed. Like basically, no matter what the second player does, if he has five matches, he's doomed to push it to a position that is winning for me, right? So what is the overall take? Six is winning or losing for the first player? Winning if he chooses one. He has a winning strategy. That is the point, right? So he can go to something that is losing for the other player. And similarly, seven is also winning because he can choose to pick two matches to go to five from where he will win. 8 is also winning because you can remove 3 matches to go to 5. You shouldn't remove like 1 or 2 matches because then you go to a position that will be winning for the other player, right? Okay, so is the pattern clear? So the question is, can you basically come up with, so you're essentially going back and asking yourself like, so, okay, let me just say this. T of I is W if player 1 has a winning strategy with I matches on the table. Okay, and it's losing otherwise. So let me just write this as true or false. Okay, so it's just easier to argue. So T of I, it's something about checking T of I minus 1, T of I minus 2, T of I minus 3. These are my possible moves, right? These are the states that I can take the game to, correct? And now how, so what do I want to say? If any of these states is a losing position, right? If any of these states is false, then I'm happy, right? Because then I can go to that state and give the other person a losing position. Is that making sense? So Raviraj says that you can see the solution building up. So that's great. Yeah. So if one of these is false, then TFI should be true. So you guys should know how to do the like the Boolean thing. I'm very bad at this. So I guess it should be like the or of the negation or something like that, right? So you negate these. So these are Boolean variables. I negate these and I take an or something. So basically, if one of them is false, right, the negation will be true and the whole thing will be true. Whereas if all 3 of them are true, like here, all 3 of them are true, right? Then there's nothing you can do. When they get negated, they will all become false. And then, you know, this current guy will be false. And you want to argue that this is really correct, right? If, you know, okay, so let's say that this evaluates to true. Okay, so let's say T of I evaluates to true. What does that mean? That means that there exists I minus 1, I minus 2, or I minus 3 for which, you know, T of, so there exists, let me put it this way. So there exists some J in this set such that T of J is false. So that means that I can go to the jth state, and if the jth state has the correct semantics, it means that player 1 starting from the jth state is going to lose, but that player 1 is player 2, right? I'm giving player 2 a losing position. So if one of these is false, then I can win. But if all of them are true, the point is that no matter what I do, the other person will win. Okay. So yeah, so here the bottom-up approach is kind of quite natural. You just build things up. But if you like, for some people, it may be more natural that they just come up with this recurrence and then determine what the base cases are. So yeah, I personally prefer the bottom-up approach, at least for an example like this. It helps to start with small examples. Yeah. Okay, so so now you just work through this. You can actually here even see a pattern, I guess, and I'm sure you can work this out too. Like, I mean, I think it's not even too difficult to work this out all the way up to 19, but even if it was a larger number, I think you can see that things are getting divided in chunks of 4, and you need to determine the remainder when divided by 4. And based on what it is, I think you can figure out if the answer is yes or no, right? Okay, so I think the thing that probably, yeah, okay, so yeah, just try to, generally speaking, think in terms of how would you break down your problem into, like, how can you leverage information from smaller subproblems to solve your current problem. That's really the mindset you want to have while doing DP. Okay. All right, so let's go on to like the next. I think 2, 3, 4, 5 are all questions of a similar flavor, but with different recurrences. So let's see, it's hopefully I don't goof up because it's been a while since I've looked at these as well. But yeah, let's just do it on the fly, I guess. So dp of I comma x is given to be So for such examples, anything that has a polynomial dependence on x, think of that as being pseudo polynomial, okay? Because that is something that's, I guess I could go into like more details about why that is the case, but from a last minute exam preparation point of view, if you get a running time that's poly and capital X for a problem like this, then think of that as being pseudo polynomial. And okay, I mean, just had to tell you a little bit about the reasoning for that. I'll do that in a second, but something, okay. Okay, so let me just briefly tell you about like, what is the input to this problem? It's n integers, right? X1, X2 up to Xn. And I'm just going to assume that you can like write down each integer with a constant number of bits. Okay. Now, right. Now you're given an integer s in particular, right? And you're doing something which is x is guaranteed to be between 0 and s. Okay. So the point is that if you are given s as input, in fact, let's even forget about x1 through xn. The reason I wrote down x1 through xn was to emphasize the contrast between this n and this s. Okay. So when I talk about being polynomial in n, I have to spend at least 1 bit of memory to write down each of these n numbers. Okay. So the input has size n because I'm writing down n units of input, right? But now I have this number s, okay, which is also written down using a certain number of bits. In particular, it's written down using log s many bits, log to the base 2, right? So that is the size of the input, okay? The size of the input, when the input is a number s, it's just log of s. It's not the magnitude of s, right? So if I write a number which is, I don't know, so let me take a number which is like a large power of 2. All right, doesn't matter. Let me just pretend that I have a really large number out here. Okay. So what is the size of my input? Is it this one? How much is this? Yeah. Let's say it's like a billion, 10 billion. Guys, somebody confirm, yeah? Billion is 10 raised to 9 or no? Billion with a B. Yeah, good. Okay. So good. So this is like 10 billion or something. Okay. So if this is your input is this number, then, if your algorithm takes time proportional to 10 billion, would you say that that's a linear time algorithm in the input? Because what is the size of this input? It is roughly like, you probably need 10 bits to write this down or something, right? I mean, this is the size of your input. This is how much memory you need to represent this input. This much memory is signifying, or it's carrying with it like a very large amount of information. But just because it's carrying that information doesn't mean you have that much time to work with it. You remember when we were going from BFS to Dijkstra, in between we had the solution where we said, you can convert BFS into a valid algorithm by taking the weight of every edge and adding as many vertices. And remember, I said this is a very dangerous thing to do because these weights can be very large. The weight of some edge can be a number like this. And if you introduce these many vertices, then though you're gone, right? I mean, then you're really introducing a number of vertices which is exponential in the true size of your input. The size of your input is like some chindi number of bits that you need to write down this number. But the number of vertices you're introducing is s, which is 2 to the log of s, right? So remember, the 2 and the log 2 will cancel, and this is s. So when your running time is s, it's really exponential in the true length of the input. That is why this is called pseudo polynomial. It looks like it's polynomial, but it's not really polynomial. It's hiding an exponential complexity. Now, for some reason, if you knew that S was at most n or something like that, then it's okay, then it's polynomial, but it need not be. And in all these other situations, it's really exponential. Okay, so that is why your high school algorithm for testing if a number is prime, right? It's not a polynomial time algorithm. How do you test if a number is prime? When you learn it in school, you say that you will try, so maybe for 2 to square root n or something. Check if m divides n. And if it does, then you declare that m is n is composite because it has m as a factor. But if it survives this test, then you say m is prime, n is prime. So this running time here, which is like n to the half, right? This is problematic because n is not the size of the input. It's the magnitude of the input. Just remember that. N is the magnitude of the input. It's not the size. How much space do you need to represent the number n? It's only log n. So you really want to think about this as n raised to log n, 2 raised to log n times half. So this is the size of the input. And therefore, your overall running time is really exponential in the size of the input. Please give me a +1 in the chat if this is making sense or if this is like, going way off. Yeah, okay. So again, pseudo polynomial, remember it looks suspiciously polynomial, but it's not, okay? Just ask yourself it's polynomial in what? If it's polynomial in some numeric input, which has been represented in a succinct way, then you should be suspicious, okay? So that's what's going on. Now let's come back to this recurrence. Here, this polynomial, pseudo polynomial will not even make a difference because you just think about how the DP table is being populated. So remember, I think what you have, this is a bit, I think, counterintuitive. The goal is to compute DP of 0, s. So I think this is like best to think of it as a 2D table. There I'll think of I going from 0 to n, and then this is flanked by like this is 0 to s. So somehow you want to compute this entry in the corner. And what you're given is dp of n comma x is 0 for all x. So these entries are all 0. So that's like your base case on the top. Okay, so let's try to compute dp of 1 comma x. This is like the first entry. For some value x, let's just try to see what this takes, okay? dp of 1 comma x. Actually, not even 1 comma x. We want to go from, so let me just pretend that n is 4. Okay. So let me just pretend that I'm trying to compute dp of 3 comma x, like that's the next row after the base case. And what is this asking me to do? It's asking me to go to dp of 4 comma s, that's fine, plus some xi, so that's okay. This is part of the input. So that's this entry here, so that's fine. But now I'm also being asked to go to dp of 0. So the other entry I have to compute is some x minus xi, which is also okay. This is fine. I can get it from the input, plus xi squared. This is also fine. I can get it from the input. But the point is that this is asking me to compute something in the 0th entry of the table, right? So 0th entry of the table right now has not been populated. I don't know what is there. So it's some garbage value or whatever, or there's some indication that, this has not been computed. So if you just go over the recurrence, what is it going to do? This recurrence is going to say that, okay, look, boss, I don't know this value right now. So how do you compute dp of 0 of something? You apply the recurrence again, right? So it's going to be dp of 1 comma something, comma, again, 0 comma something, right? So the point is that if you look at how the recurrence tree will pan out for 4 comma s, for 3 comma, so we said we'll try to compute this entry 3 and x. So for dp of 3 comma x, you will look up, on the one hand, you will look up dp of 4 comma x. But this side, you will look up dp of 0 comma something. I don't know what that something is, but it's not been computed yet. So that's going to be dp of 1 comma x because you have I plus 1. But again, it'll be dp of 0 comma something. Okay. And then this guy again will be dp of 1 comma something and dp of 0 comma something. Okay, so hopefully it's clear that as you unravel the recurrence, this is never ending, right? The 0 entry will keep getting called upon. Okay. In practice, when you implement this as an algorithm, depending on which language you're using, maybe this dp 0 comma x will get called, will actually return some garbage value, okay, which is not intended. But if you, this is memoized, so this will actually just go deeper and deeper in the recursive stack, and it'll keep getting stuck. Okay, is this making sense that this is infinite? That's why one of the things we said also in the videos was to be very careful that whenever your recurrence is appealing to values, smaller values of subproblems, you have to make sure that those subproblems have been computed at the time that they are being invoked. Otherwise, you will get into this sort of a endless loop. Yeah. Okay, great. Yeah, it's great to hear that it's making sense. As I said, whenever you see a recurrence like this, try to unravel it for a few steps, like draw the table, draw the whatever picture, and just try and see what will happen if you try to compute, some value. Right. Okay, so let's go on to the next one. This is number 3. So dp of question number 3, dp of I comma x is max of dp of I plus 1 comma x plus something plus xi, and dp of I plus 1 comma x minus xi plus xi squared. Okay, so here again, if we draw the same picture, you'll see that this is kind of okay in the sense that you can systematically fill out the table. This is I equal to 0, I equal to s, I think, and sorry, I equal to n, and this is x going from 0 to s. This is the entry we want to compute, and these are the initial base case entries, right? Okay, so now you'll see that for computing any dp of I comma x, if this is your entry, you are only invoking entries from the I plus 1th row, right? So the row above. So to compute this entry, I'm looking at some entries in this row, correct? So I'm in fact poking 2 entries in the row above, right? But these could be, since you're computing, so at the end, you want to compute dp of I equals 0 comma s. So this is going to be, for example, so what would dp of I equal to 0 comma s? Sorry, this is the entry you want to compute. So that'll take you to dp of 1 comma s plus x sub 0, I guess. You're given, okay, so this actually is n minus 1. I should correct this. And on the other hand, you're going to have dp of 1 comma s minus x naught, whatever that is, plus x naught, and so on. So once you have that, you know that you're poking these 2 entries, and these entries in turn will require you to poke another 2 entries, and so on and so forth. So so the point is that your the number of entries that you compute, on column wise, of course, you are going to go through and invoke n minus 1 entries, but the total number of entries you compute in the worst case can be as bad as having to compute most entries for every column. Okay, so essentially there is a dependence on S, because these intermediate values that you're looking at, right, they could be any values between 0 comma s. You don't really have control over it. You don't have a way of bounding the number of like the number of values on the second index that you have to compute. So a perfectly valid upper bound is n times s, because each entry in this 2D table is computed at most once. So n times s would be a valid and I think a reasonable upper bound. By reasonable I mean tight, because I'm sure you can come up with inputs for which you'll have to painfully compute a lot of entries in this table. So here, because the best upper bound we can come up with has a direct and linear dependence on s, we are going to call this pseudo polynomial. Okay, and I think the contrast will become clearer when we see some of the examples where it is where it is polynomial as opposed to pseudo polynomial. Okay, so let me pause and ask again, is this fine? Is this is question number 4 okay? Sorry, this was question number 3. Question number 3, is this fine? Great. All right, thanks. Perfect. So now in contrast, let's take a look at this example where we have, I think this one should go a bit faster. dp of I comma x is dp of I plus 1 comma x and dp of I plus 1 comma 0. Okay, again, some plus something from the input. So I'm not even counting all of these operations because this is just like constant time looking up of the input and some arithmetic. So that's easy. But now again, think about how the recurrence is going to appeal to the values in the DP table. You're starting off with we said I equals n minus 1. You're trying to compute this entry here. So this will ask for this entry here and this entry here. This in turn, to compute this and this, the two entries that you will need are again the entries from the upar wala row, the row just above, but again from the extreme columns, right? So for computing, say, dp of 1 comma 0, you need dp of 2 comma 0 and dp of 2 comma x. To compute dp of let's say, what is this, s comma 0, I again need okay, so sorry, I should say not s comma 0 but 2 comma s. I think I'm using the first coordinate to talk about the row and the second coordinate to talk about the column. So to do, so let me just use a different color here to sound a little less confused. So dp of what is this? First, like I is 1 and the column is s. So dp of 1 comma s, again, what is the recurrence? We are going to be needing dp of 2 comma s and dp of 2 comma 0, right? So in fact, we need to compute both of these entries, we need the same set of two values from the row above, right? So once again, these are the two entries that we need to compute. So really, since you only make the calls that you need when you are doing memoization, this is going to be, n entries that need to be computed on both of these columns. So the computation is roughly proportional to 2 times n or order n. Okay, so in that sense, it's truly polynomial. Okay. So Raviraj, the reason for pseudo polynomial in the previous thing was that the running time depended on s, where s is just a number given to you as input. So it's one of these things, right? So s could be this big number. And if your running time is proportional to s, then the running time would be considered pseudo polynomial. That's what we were discussing earlier. Then come back and clarify this further if you would want me to. But in the meantime, is question number 4 being polynomial okay? So notice that you avoid this. I mean, this picture is not to scale, okay? If I really had to draw it out, it would probably be something like this. Your DP table is short and wide because these values of x ranging from 0 to s, like s is huge, okay? And I is going from 0 to n minus 1. This is really, I mean, n is something you really have as input. You have in your memory, you've written down n integers. So you've definitely used n bits to express your input. So n is the size of the input. And the size of the input is something like n plus log s, right? So when you're writing down a table that is s units wide, this is an exponentially large table. Okay, that's why, you know, when we do top down, if we were trying to implement this deeply top down, sorry, if we were implementing it bottom up and we would write out the whole table and try to populate everything, you know, even declaring this whole table may be prohibitively expensive, right? So that's one situation where maybe using bottom down is better. Top down is better. There is nothing called bottom down, sorry. So using top down would be better because of the fact that you only call the entries, you know, you only invoke the calls that you need here. Okay, so okay, so let me know in the chat if this polynomial analysis for question number 4 is okay. All right, great. Thanks. So now we're left with question number 5, at least in this category. So here what we're doing is there's a very explicit computation here in the recurrence itself, where we are saying that, you know, we are computing for every subset of, you know, x naught to xn minus 1, we are computing something. So dp of I plus 1 x minus summation s, the summation s the whole square. Once again, this is not you know, this is a valid recurrence. It will systematically take you, whenever you're trying to compute an entry in the ith row, it will only ask for some values of entries from the I plus 1th row. But to even compute one entry, you have to take a minimum, or a maximum. So I did not actually write down, I did not write down the aggregator. So this is a max over all of these entries. The max is over, this max is being taken over all subsets. So even to compute the max, you have to consider how many entries, how many over how many numbers are you taking a max. So there are n things and you're considering all possible subsets. So, so this max is being computed over how many numbers? Anybody? 2 to the n, correct? So because there are 2 to the n subsets of n objects. So this max itself, like you're doing 2 to the n many probes into the row above you, right? So it's definitely not a polynomial. Like this running time, even to compute one entry, is not bounded by a polynomial function, right? You could say that because we're doing, you know, x minus something something, we also have a dependence on s, and that is true. So if you have to choose between pseudo polynomial and exponential, I would say in some sense the exponential bound is okay. Technically you could say that they're incomparable because depending on how bad s is, you could probably say that. So s is also in some sense, you know, there's a sense in which you could think of it as exponential, right? So s is also exponential, but you know, the terminology in the literature to refer to these kinds of running times is pseudo polynomial, just to remind ourselves of the fact that first of all, the running time does not look exponential. It looks polynomial, but it really isn't. And also it becomes polynomial if s is bounded, whereas this, you know, there's no question of like, there's no situation in which this running time is polynomial. It's just exponential by design. You're definitely going to spend exponential time. So if you have to make a choice between describing a running time as sort of polynomial or exponential, commit to exponential, at least in the context of our course. If you were in a job and you had to explain the running time, I think you should explain all aspects of it and not try to come to one answer and like you're doing in an MCQ. But here the logic is that typically the exponential running time would dominate the whole thing because that's the most expensive affair here. Because with s, though there is some chance that at least if s is small, you may get away with its being polynomial. So, but here really you're spending an exponential amount of time for sure, and you think of that as being the dominant factor in your running time. So that is why this is exponential. So does this also make sense? Please tell me that it's okay. But no, I'm just joking. If it's not making sense, we can go over it again. But give me a +1 in the chat if you're fine with question number 5. Okay. So, so yeah, I mean, if you get a question of this kind, typically just like the exponential will be easy to pick out, because whenever you have like, having to go over all subsets or something really stupidly expensive like this, it is exponential, right? So that's easy to identify. To distinguish between infinite and the rest of the options, just carefully check if the algorithm is doing something that involves getting into loops, right? So self-referential endless loops, that would be indicative that it's infinite. And to distinguish between polynomial and pseudo polynomial, just carefully see if you're able to get some straightforward bound like this, where the computation really is constrained to some polynomial subset of entries, then you can say that it's polynomial. Otherwise, pseudo polynomial would be a safe bet if you see a dependence on S come in somewhere. Okay, so fine. So that addresses these questions. Now, given the time we have, I was thinking of doing the question from week 12, like maybe not the specific numbers necessarily, but just how to solve the problem. Would that be of interest to everyone, or do you want me to do something else? Because I remember right in the beginning, I think somebody said that question 12 would be a good idea to cover. So that's what I was thinking. And it won't take too long. It's not very difficult, I think. Week 11, I think from like my idea was to give you a collection of cute questions, which were not hopefully very difficult. But if anything was unclear in terms of either the terminology or the recurrence, then let me know. But I think somebody said they'd solved week 12. If we had a little more time, I would really just invite you to explain your solution. In fact, if somebody would like to pitch in, please feel free to like unmute yourselves at any point of time. But here, I'm just going to go ahead and at least get it started. So remember, what you want to do here is you have been given you've been given n boxes, and they're labeled 1 to n. And you have k toys. And you have to distribute these k toys into these boxes in such a way that every toy goes into exactly one box. So some boxes may be empty, that is fine, but a toy cannot be shared between two boxes. And also every toy has to go into some box. Nothing can be left out. Okay, so the question was, what is the number of ways in which this can be done, right? And there were some examples given in the question just to hopefully get a feel for the different settings. Now, okay, our DFS BFS will do week 9 as well a little bit. Yeah. Okay. So here so I'll skip the examples because we had kind of discussed it in the previous live session as well, and chances are that all of you have looked at it. So let me just skip ahead and tell you what the DP should be. So let's say we do DP of ij as being the number of ways you can distribute I toys into j boxes. Yeah. So just think about what's like the most natural way of capturing some sort of a intermediate snapshot of your problem. Okay, at least first level DPs are usually like this. Like, what's a natural, you want to do something for n, how would you do it for I? If you want to do something for like things that have 3 moving parts, just try to convert them into indices and see if they correspond to some natural sub problem, which is just like a miniature version of the original problem, and then see if that also leads you to the final answer. So here, for instance, if I substitute k for I and n for j, then what do you get? The number of ways you can distribute k toys into n boxes. So this is the answer that you want. So if you can compute all of these intermediate values, then you would be happy, right? And the base case is also kind of easy. So for instance, if you want to distribute 0 toys into any number of boxes j, you could think of it as doing nothing, and you could think of that as being one way of doing things, if you like, just to do nothing. But if that's confusing, you can ramp up your base case and say, okay, and how many ways can I distribute one toy into n boxes, right? Well, then there are n ways of doing it because the toy has to go somewhere and you just have to choose which box it goes into, right? So that is as long as j is at least 1. As long as, yeah, I mean, n is at least 1, you're kind of happy to do this. So in general, actually, I should just say that distributing one toy into j boxes, there are j ways of doing it as long as j is at least 1. Okay. So, and if you have one toy and no boxes, then of course you cannot do it at all, and you can say that the answer to that is 0. Okay, so those are the base cases. Now the main thing, of course, is the recurrence, right? So just think about if you have j boxes. By the way, I forgot to say it, but every box is a capacity also, right? So the jth box can handle maximum aj toys. Okay, so let's look at this last jth box here. And if I think about all the ways in which you can distribute I toys into j boxes, all these valid distributions, in some of them, the last box will have 0 toys. In some of them, the last box will have 1 toy, and so on. And some of them, the last box will have AI toys, where, this is the jth box, so AJ, so the box is full, right? So in some ways of doing this, the box is full. You could take AJ, or, this is really not AJ, let me call this AJ prime, where AJ prime is min of AJ and I. So if AJ is bigger than the number of toys that you have, then some of these will not make sense. Some of these sets will be empty. So, let's just consider this still there, right? So if I want to count the number of solutions that have this form, that put no toys in the last box, can I get it from something that I've already computed? Anybody? What is the number of ways in which you can distribute I toys into j boxes, given that no toys go into the last box? Then that is the same as distributing what? I've given you a visual hint also. Right, dp of I minus 1 j. So now the number of boxes has gone down by 1 and is still stuck with the same number of toys to distribute. So I guess, let me just clarify. I toys into j minus 1. So it's going to be the same I toys actually, because we didn't put anything. I think your indices, Raviraj, I'm just going to switch them. Okay, so yeah, dp of I j minus 1. Number of boxes has gone down by 1, same number of toys. In general, if I put some k toys in the last box, you can probably guess that the answer for this will be in dp of I minus k, because that's how many toys you're left with, and j minus 1, right? And, so k ranges from 0 to aj prime, right? Because that's the aj prime is a decent limit on how many toys go into the last box. It's either aj or I, whatever is smaller. Okay, right. So yeah, cool. So this is essentially the entire recurrence. You just have to take the sum over this. So let me just write it down once to recap. So dp of I comma j, where I is number of toys, j is number of boxes, is the sum over let's say k, going from 0 to min of I comma aj being the limit of the first box, dp of I minus k and j minus 1. Yeah, is this okay, everybody? Okay, give me a +1 if this is fine, and then we'll move on. Cool. Great. Awesome. Right. So let's talk a little bit about I guess, fourth full person, week 8, week 9, and flows. I think before that, I think for those, I don't know, maybe some of you have to leave because it's 8. And then I think somebody had asked what would be a strategy to score 50%. Actually, itna though I've not thought for my own exams also. Yeah. So I really, I don't know. And I'll be perfectly honest with you, this exam paper was written like months ago, even before the course, like took off the ground. And I think we just had to make some modifications in it to make sure that it's at par with the material that we are actually teaching. But other than that, I honestly don't even have a good memory of what is there. But I would say in general, there are many questions in the paper that just involve thinking on your feet. Okay, you can do it with almost no preparation. Like if you've generally been practicing, you should be completely okay. So these are either ad hoc problems or these are problems where you have to read a certain problem statement and, basically work out small examples and things like that. So those should be like the lowest hanging fruit. So take those first, and this requires almost no preparation. The other kind of thing is, I think there are some problems which are either very similar to the assignment problems or exactly the same as assignment problems. Not too many of them, but there are some. So make sure that, those should be okay. So just go over the assignment. Like now, you have questions, answers, everything. And I think you'll get an announcement about the corrections. I'll also post it once on Discord. That is my bad. I think there were some questions whose answers were corrected. So please go with the corrections. I think the corrections came from you guys only. We had made some mistakes in like 3-4 of the assignment questions. So I'll summarize those for you. But yeah, make sure you take a look at the assignments. I think that is one small thing that is doable. Other than that, I think you should get a good night's sleep. Okay, it's like completely crazy to show up to an exam without sleeping properly. Okay, so that would be my advice right now, to chill. I think your preparation so far has, I'm sure it's there in your subconscious. So I would say coming well rested is much more important than cramming anything, than coming without having adequate rest. You might find that the exam paper is a bit on the longer side. I'm not very sure. I've never done this before for this course. So I'll have to calibrate based on your feedback only. But, as I said, some of that was in the hope of also being able to create some easy questions apart from like regular questions. I would say, other than that, I wouldn't say like one topic has more footage than another topic. And so you should read this week more, that week less, kind of thing. I will say that questions that are like directly invoking your memory, like, what is running time of bubble sort and all, such questions are either very few or practically not there. It's really more about giving you scenarios. And so my hope was that the experience will be very similar to the combination of doing a programming contest, except it's like you're doing it on pen and paper. So half of it will be like that. The other half of it will be like a revision of your assignment problems and some problems that are similar to assignment problems. Okay. So that is the intended experience. If you cannot finish it within the given time, then, don't judge yourself. It's just me not being able to correctly estimate how much can be done in a certain period of time. So but go with it with the mindset of doing an actual competitive programming contest. Okay. The questions were intended to simulate that kind of an environment, right? And to be honest, I don't think there will be much from max flow kind of thing. In a contest, I think that's one of the harder kind of problems to work with, because you have to come up with the right modeling, then you have to quickly, properly create the graph. After that, your library, your predefined flow function, like you're not going to code up max flow during the contest. Hopefully you'll have the code with you ready. So after that, it's not difficult, but coming up with the right model requires imagination, right? So I don't think there will be much to worry about on max flow in that sense. But for example, if there's okay, so with Maxflow, I will say the important things to remember are the definitions of like what a flow network is, what is the definition of a flow, and like the main idea of why, when you just try to, what do? We say that you have like a designated source and sink, right? And, we sort of try to say that you push a flow from S to T along a path in the residual graph. And I don't know if you remember from the videos, what we said is that you build this residual graph, you look at the edge which has the smallest capacity among all the edges in this S2T path. We call this the bottleneck capacity, and we try to push a bottleneck amount of flow through this path. Then we reduce all the capacities by B, right? And if you just keep doing this, notice that you may miss out on getting a max flow if this is all that you do. So the important thing to remember is that just the greedy flow the greedy flow algorithm will not work. If you just try to keep greedily pushing flow by creating S2T paths and reducing capacities, you can come up with examples where it will not work, right? And I think we have seen such examples, quite a few of them. So, you have this sort of an edge and you first push this flow and then you get stuck, right? So we've seen this sort of thing. So that's why you need this concept of a proper residual graph where you introduce this really clever concept of a back edge and things like that. And after that, so after that, I think what we said was that if you simply run Ford Fulkerson, which is that you create this residual graph, compute the residual capacities and just find some ST path and push flow through it, then the running time can be as bad as the max flow itself. But on the other hand, if you use BFS and always find a shortest path, and that is, I think, Edmonds Karp, then you get a running time which is much nicer. And I think it's just it's NE squared or something, and M squared, I think. And now you can improve this using Dinnick's algorithm further to N squared M. You don't have to worry about Dinnick's algorithm at all because we did not cover it and it's not there in the exam. But Ford Fulkerson and Edmonds Karp, I think it's just useful to know that, that's what it is. Okay, so M squared N, exactly. So basically you remove the dependence on the, on the max flow, which in turn could be a function of the capacities. And again, you have this polynomial, pseudo-polynomial difference, right? So if your capacities are arbitrarily large numbers, then your max flow could also be an arbitrarily large number. So having a dependence on the max flow is like scary, right? So it's, again, something that you could think of as a pseudo-polynomial running time. So that's not good. So again, Edmonds Karp, why does it work the way it works? That was something that we did not discuss. It was originally a part of my plan to cover a bit of the argument for that, but we don't do it. So again, don't worry about it. What is more important in max flow than the algorithms is something that, so technically in this course, we think of most of the algorithms as being prerequisites. The focus is really on coming up with, good implementations and then really solving problems, right? So for max flow, I think the thing to emphasize or remember is how do we model other problems as max flow problems. So at best, and you can imagine, right, in an MCQ question, I cannot ask you to come up with a modeling, right, because that would be a subjective answer. So I will end up probably, just like we did with the assignments, proposing a model and then asking, okay, what should be the capacities here? How should we do this? How should we do that? That sort of thing. So I hope that the assignment questions and answers made sense. If anybody wants to revise any of the assignment questions from weeks 8 and 9, let me know. We can go through that right now. In fact, because I also felt that this may be a slightly challenging topic, I think I kept the assignments very close to the video material. So I think the cricket elimination problem featured in one of the assignments as well. So I think you can, if that was confusing, maybe going back to the video will be helpful. But what else? So do you want me to cover anything specific from weeks 8 and 9? Then let me know. I'm happy to discuss it specifically. Ravi Raj, no. You don't have to do specific programming questions. So there are some new programming questions that will be there in the exam. You've not seen them before, so revising these questions will not be particularly helpful. I will say that any practice that you may have done will generally help because you have a problem-solving mindset. Okay, so that is all that I will say. But you don't so something very specific from the lectures will not come up. Even if by chance it is there, it will be there with the full context of the problem, right? So we will recall the problem definition and it won't be out of the blue. Okay, so that is for sure. Now, okay, week 8, 5th problem. Let me see if I can find that. Okay, is this the one where we say given a flow network, how will you determine if F is a max flow? DFS, BFS, can you confirm? Okay, all right, yes, okay, cool. Let's go through this then. So, right, if there is, so somebody gives you a flow and then there is an edge that is not saturated fully, then we can conclude that F is not a maximum flow. So let's maybe do an example to see why this is not correct. There's no suspense, right? You already know the answers. So let me just try and justify the answers. So for instance, you could just have a graph like this, SD and intermediate vertex X. This capacity is 1 and 2. So the flow is going to be flow equals 1 here, flow equals 1 here, because the conservation law has to be respected at X. You cannot do any better. The max flow is 1, but here you have an edge which is not saturated, meaning it's not being used to its full capacity, but this is still a max flow. So it's not true that if there is an edge that is not fully saturated, we can conclude that F is not a maximum flow. It may seem tempting that if some edge is not saturated, there is some scope we are missing out. We can push even more flow through this edge, but that's not true, because to push more flow through this edge, you'll also have to worry about the repercussions, right? On both sides, you have to worry about conservation constraints. So even though you may not violate the capacity constraint on that edge, you may violate conservation constraints. Okay, so that's why this is not true. If the residual graph does not have any augmenting paths, then F is a maximum flow. This is by by the definition of how the algorithm works, right? So you go to the residual graph and okay, so you want to understand these terms, augmenting path and residual graph. Okay, so let me try to do that once. So, okay, we define flow network. You have a flow network G. So for every edge UV, you have some capacity, okay? And you're also given a flow function F. So you have the flow going through this edge E as well, okay? So for G comma F, for this pair, you can define a residual graph G comma F, which basically gives you, so if there is an edge from U to V in the residual graph, you will also have the edge from U to V, but you will have a residual capacity going through this edge. You won't have the full original capacity. What is the residual capacity? By residual capacity, we mean what is the remaining capacity. So you look at the original capacity and you remove the flow that is going through it, okay? So if the original capacity was 50 and the flow going through this was 20, then the residual capacity is going to be 30. This just means that there's 30 units left. That is how much more flow you can send through this if you want to, right? So that is residual capacity. And then we introduce these back edges, which is like the best part of the residual graph. So we also introduce an edge from V to U, and the capacity of this back edge is going to be equal to the flow that we push, okay? So you might want to recap the video once where we explain why we're introducing these back edges. It's basically to give us a facility to correct any mistakes that we made, right? So if we push, if we pushed a flow of 20 units through the edge UV, but then we decide, oh, okay, we shouldn't have done that. We should have only pushed 10 and we should have pushed another 10 units in some other direction. That can happen. And so when you take a SD path in the residual graph and it involves a back edge, that's basically a way of saying, let us reduce the flow going in the corresponding natural edge based on which this back edge was introduced. Okay, so that is, so that's the residual graph. Okay, the residual graph is just built from an original flow network and a flow. And you basically introduce two edges for every edge in the original graph. One is the normal edge, and the capacity is the capacity minus the flow. And then the other is a reverse edge, which goes in the opposite direction, and its capacity is equal to the flow. So this graph is called the residual graph. And any path from S to T in the residual graph is called an augmenting path. This path could use either the natural edges or the artificially introduced back edges. It can use a mix of these edges, but every time you push a flow through such a ST path, what you do in the original graph will be different depending on whether it was an original edge or a back edge. Okay, so so I hope that clarifies to some extent. If in the residual graph you have a ST path, a path from the source to the target, it's called an augmenting path because it helps you increase the flow by passing some flow through every edge in the augmenting path. Yeah. Okay, perfect. All right, great, thanks. So, so this algorithm basically stops whenever S gets disconnected from T in the ST path and in the residual graph. So that's why if the residual graph does not have any augmenting paths, that means you're done. You've found the max flow. We have not discussed the correctness of this algorithm, but we have discussed the mechanics of it. So you just have to believe that it's correct or you know it from before. But essentially, it is true that when the algorithm stops, you get a max flow. And that's why the second option is true. Let's just look at the next two options. If the value of the flow F is not the sum of the capacities of the edges coming out of the source, then F is not a max flow. Again, not true. Very easy to come up with examples where you know, the source vertex, you know, has so you could have this vertex with a capacity of 500, but you know, this edge that's next to it has a capacity of 1. So the maximum flow in this network is just 1 because this is the bottleneck edge. Okay, so just because you were not able to saturate things coming out of S does not mean that your flow is not a maximum flow. And it's the same argument for this for the fourth option. You can just repeat this example, except make the edge incident on T the one with the higher capacity, right? So just because you cannot saturate edges doesn't make your flow not a max flow, okay? All right, Raviraj, you're saying week 8 last problem. Is this the one about the mice and this thing? The mice and somebody catching the mice, I don't remember. Right, so suppose there are M mice out in a field, there are edge holes. So let's see, I think the approach will always work is what we wanted to say. And what is this approach? Right, so there are edge holes M mice. And I think you have their initial positions as well. So you know where every mouse is, I guess. You know their velocities at which they can travel. And you know that, you know, at some point the owls are going to arrive. And if a mouse has not found a hole within S seconds, then that's a problem, right? When the owls come, they will catch everybody who is not hiding, okay? All right, so how do we model this as a flow problem? So let's say that we want to get the mice safely into their holes. So we're going to have, let's say, a graph like this. One vertex for every mouse. So this is M vertices here, and one vertex for every hole. So H vertices here. Now, we want to add an edge for a particular mouse to a particular hole. When do we add this edge? We say that, okay, let's look at the velocity of the mouse. Let's look at the distance of the mouse at position, like at time t equals 0, the mouse is somewhere, the hole is somewhere. So you have a distance. So, and you know the velocity of the mouse and you know the time. So you know that you have S seconds. So you just ask yourself, can the mouse travel this distance and reach this hole safely within S seconds? If the answer is yes, then you add an edge from M to H. If the answer is no, then you don't add this edge, okay? Is the construction so far clear, how this graph is constructed? Okay, super. So now what we want to do is, okay, so these are edges that we're going to have with like capacity 1. And now what we will do is, add an edge to all the mouse vertices, like add a source and add a sink from the holes, or add a target from the holes to like this vertex, and add a source that sees all the mouse vertices. Okay. And now what's interesting is the capacities of these blue edges. So here I'm just trying to say, okay, can this mouse be saved? So this is just 1 unit of flow through these edges. So the capacities here will be 1. But every hole, we are told, has a certain capacity HI. Okay, so this hole may have a capacity of accommodating some 50 mice. So what should be the capacity of this edge intuitively? Just think about it, like what's your gut feeling? What should the capacity of this edge be from the hole to the sink or the target? HI, yeah, exactly. For a minute there, I thought you were saying high, but okay, yeah, it'll be 50, or it'll be whatever the capacity of that hole is, okay? So, right. So now what we want to argue is that let's find the maximum flow here. The maximum flow here will saturate some of these edges, right? And I claim that each one of the edges that is saturated by the max flow correspond to mice that can be saved, because remember that, uh, the incoming flow into any mouse vertex has to go out somewhere. That's by conservation. And all the flow that is landing at a certain vertex corresponding to a hole, all of this flow also has to get out, and the only place it can get out is to the target. And because that has a capacity corresponding to the capacity of the hole, we know that every hole is receiving only so many requests from the mice side, right? It's no more than its actual capacity of hosting a certain number of mice. And the fact that all of these mice can reach their designated holes also follows from the fact that that's how we added the edges. So if one hole was not accessible for a certain mouse, we would not have added that edge, right? So if you have a flow which saturates some k edges incident to the source vertex, then these k mice can certainly be saved. And the saving strategy will simply be ask all the mice to go to the holes via the edges that are saturated by the flow. Okay. So that's one aspect of it. The other aspect is if there is some strategy for the mice that helps like some T of them to get saved, maybe T is not a good thing to use because I already have T as a vertex. So let's say you have some strategy that will save Q of the mice. Okay. So then I can build a flow around that of value Q as well, because I can just ask you, okay, according to your strategy, where should this mouse go? So first of all, I'll ask you, which of the Q mice are you saving? You'll say, okay, I'm saving the first one, the second one, and the last one. And I'll say, okay, according to you, where are you sending the last mice? You will say, okay, it's to this particular hole. And if your strategy is correct, that must be an accessible hole. Otherwise, your strategy is anyway fraud, right? So if your strategy is correct, I must have an edge like that. And I'll ask you for your strategy for every mouse, and I will push the flow according to your strategy. And now I will just complete the flow, and I should be able to complete it, because if I get stuck, I mean, I'll anyway not get stuck on the left side, because that's just, trivially extending these mouse vertices back to via these capacity 1 edges. On the right hand side, it's a little more serious because these edges have a certain capacity and a hole may be getting a lot of incoming flow, but that's still bounded by the capacity of the hole, and therefore the capacity of this edge, because your strategy was a valid strategy, right? You would never push more mice to a particular hole than it can accommodate. So if you have a strategy, it can be translated to a flow. If you have a flow, it can be translated to a strategy. So the best strategy that saves the maximum number of mice corresponds to the flow of the largest value. Does that add up? Does that make sense? Yeah. And if you're wondering, like, where did we use the velocities and the times and so on, it was in the construction of the graph. Okay. So these edges between the mice and the holes, we added them carefully, keeping in mind the calculation with regards to the distances and the velocities and so on and so forth. Okay. So yeah, I mean, if at all you have, questions around max flow, it'll either be, things about, like, if I, about the logic of max flow, or it will be about, like, modeling problems like the one you're seeing here. So yeah, I mean, I would say in terms of absolute last minute practice, I think it may be a good idea to just go over, like, typically at the end of the theory lectures, we have like a table or something at the end where we say, okay, if you use an adjacency matrix to implement BFS, this is how much time it'll take, and things like that. So yeah, I mean, maybe taking a look at those, or taking a look at the assignment questions, these would be good things to do in the last minute. And I hope that some of this pseudo polynomial, exponential polynomial business with BP was clarified. Yeah, I think, as I said, it's already getting like a little bit late. I don't know when the exams are. Are they tomorrow or on Sunday, or like when are you giving your exams? Those of you who are still here. Sunday, okay. 24th, okay. So that's not too bad. You have like, you have another day to take some rest. And I would say, yeah, then, I mean, assuming you have no other plans on Saturday, I would say just look at the assignments a little bit, look up like the overall, like the concepts. And yeah, I would say definitely don't bother with like going through the solutions to specific problems. I don't think that's very helpful. But just go over the concepts, kind of the running times. It's a good idea to remember what algorithm has what complexity, at least, at a high level, just the algorithms that we have seen. And mainly really, yeah, I mean, for example, when we were doing things like, say, greedy or, even ad hoc, there's nothing specific to remember. It's only really with graph algorithms that it starts. So BFS, DFS, Dijkstra, Bellman, Ford, Floyd Warshall, Prims, Kruskal's, Ford Fulkerson, Edmunds Karp. I think these are the running times worth remembering. So about a dozen of them. And then again, greedy DP is more strategy based, so you can just do it on the fly. And yeah, maybe a good idea to recap some sorting running times. That's about it, I guess. And yeah. And yeah, of course, disjoint set. So remember what happens with and without path compression. I think those were some of the assignment question answers which were messed up. So I will update Discord with like the correct answers, I guess. So cool. Yeah. All right. So yeah, I think I've kept all of you here for quite some time. I hope this was helpful. And yeah, I guess I'm just trying to see if there's anything I missed when I rattled off the list of the algorithms that you might want to, like, just remember at a high level, what problem are they solving and like how much time they take. I think that was about it, really. Did a bunch of graph algorithms and so forth. Week 9, last question. Let me take a look. Okay, this may take like 5 minutes or so to explain. So I hope you're good with staying back. By the way, those of you who are getting late, please don't feel obliged to stay or anything. I just wanted to wish all of you best of luck and thanks for joining and staying back all the way. And to Raviraj, I'll just request you to hang around for like 5 minutes if you want to go over this. So this is actually starting from, yeah, okay. So we're starting from a question where we have, okay, let me just recall the question because again, it's been a while. So we have n weights. Positive or negative, never zero, right? And you want to choose a subset of these weights so that the sum is maximized. And I think you have some implication constraints which says that if you include X, then you must include element Y. Implies Y. Okay. Right, and then there's a bunch of examples, blah, blah, blah. Okay, consider the case when we have just two elements, X and Y, with weights P and minus Q. Okay, maybe helpful to do this maybe with a concrete example, or I guess, okay, okay, so I think maybe I should go through the definition of the flow network as well. Sorry, I just don't have this question off the top of my head, so I'm just trying to. Okay, so we have like P and minus Q, and we are choosing a large number B. So we are saying B is P plus 1. And our flow network, we have vertices X and Y. I hope this is like the right question. Okay, so you're saying week 9 last 4 questions. I somehow assumed week 9 last question, so I just jumped into that. But okay, so in fact, then let me just go back to the beginning. So I think if you like get the hang of one of them, you'll also get the hang of the rest. But yeah, let's see. So so we have a source vertex S and a sink vertex T. Want to introduce a vertex for each element in the set. We'll typically always be dealing with 2 elements, I think. So I'll just leave it at 2 elements. And we will have an edge from the source to each node with a capacity of B. So B is like some number that is bigger than the max weight. So typically it'll be something like max weight plus 1. And if you have an implication from X to Y, you will have an edge like this with infinite capacity. So we'll just keep that at the back of our minds. We'll see how things work out in the actual examples. Now the capacities here are B minus weight of X, B minus weight of Y. Okay. So does construction make sense? Okay, cool. All right. So okay, let's look at the 7th question then. 7, 8, 9, 10, I guess. Yeah. All right. So okay, so is it possible that both of these edges are saturated for a given element, right? Right. So okay, so let me say that this edge here will have a capacity. So okay, basically what I want you to think about here, I think, is you have this, right? This is some element V, and then you have this edge to T. Okay, so this capacity is B, and this capacity is either more or less than B. Okay, so if V has positive weight, then this capacity will be less than B. So if B is positive, so this capacity will be less than B. And if V is negative, then this capacity will be greater than B. Do you agree with that? Just by this is from the definition, right? Okay, sorry, this color is a bit jarring. I'll fix that. Okay, I hope that yes was for this part. Okay, all right. So either way, the question is, what is the bottleneck edge? So here, this is the bottleneck edge, and here, this is the bottleneck edge. right? So if we want both of these edges to be saturated, then what I mean, the point is that here you're pushing, when v is positive weight, you're pushing more than this guy can handle. So this is like, it needs to get out somewhere. And here, if this has to be saturated, if this second edge has to be saturated in the case when v is negative, then you need more incoming flow for this edge to be saturated. So S to V alone will not be enough to supply flow to the intermediate edge. Okay, so let's just read the answer. Provided either V has positive weight and has an infinite capacity edge going out of it, or it has negative weight edge, it has negative weight and it has an infinite capacity edge coming into it, right? So those are the two cases that we just discussed. And infinite capacity edge is understood because other than the edges from S to T, any other edge incident on V will be by construction an infinite capacity edge only, right? Okay, so that's question number 7. Did that make sense, or do you have any questions about that? It's okay. All right, cool. Fine. So now let's take the case when the input has no constraints. So there are no intermediate edges. You just have a collection of elements. Nothing is forced, right? The total weight of all the positive elements is P. The absolute value of the sum of the weights of the negative elements is Q. What is the value of the maximum flow in the network? Okay, so how do we do this? Well, so there are no other, okay, maybe I should have just left that alone. I'll just start a new page here. So you have a bunch of elements. These are the positive ones. So and let's say these are the negative ones. So from the positive ones, remember the outgoing edges are going to be the bottlenecks, right? And for the negative ones, the incoming edges would be the bottlenecks, right? So here, whatever the value is, whatever the capacity is, so let's maybe do a small example. So let's say you have 5, 4, 3, 2 as the positive edges and -1, -2, -3 as the negative values. So let's say B is chosen to be something like 6. So all of these edges have capacity 6. On the other hand, these edges will have a reduced capacity, in this case 1, 2, 3, and 4. Whereas these edges will have an increased capacity. The capacity will be 7, 8, and 9. Okay, so what is the maximum amount of flow that you can push? Well, I mean, on this side, you can only push like as much as these edges. Remember, there are no cross edges coming to your rescue. And here, again, you can only push as much as these bottleneck edges, right? So in some sense, you could think of it as trying to push n times b, that's all of this, but these guys are spoiling the fun for you a little bit, right? So it's essentially, okay, I mean, it depends on what is more convenient to calculate, but you are essentially taking out a value of P from, that's the total amount that you subtracted, right? From here, you subtracted 5, from here, you subtracted 4, here you subtracted 3, and here you subtracted 2. So the total amount that you subtracted from this flow that you could have potentially taken up is P. Okay, so that's the maximum flow that you can push. Okay, so that's question number 8. Is this making sense? Okay, all right. So for the other two questions, I think basically you're dealing with a case when there are two numbers. So there is, one of them has a weight of P, the other has a weight of -Q. And so B is P plus 1. So this is P plus 1. This is P plus 1. This is P and Q, and let's say that we have the constraint X implies Y. So if we take the positive guy, we also have to take the negative guy, okay? So that's our constraint. So this edge has capacity B minus P, so that's just 1, I guess. And this is P plus 1 plus Q. So correct me if I'm wrong on any of this, but I hope that that's okay. These vertices, I think we called X and Y. Sorry, for some reason, my iPad does not seem to be working, registering strokes properly. So the handwriting is super weird, but we'll hopefully manage. Right, so I'm looking at question number 9. So what we are saying is, suppose Q is greater than P. So the negative quantity is, overbearing, right? So what we are saying is, what sort of a flow do we have? Right, so here I think, and the next question is also similar. So maybe let's do this one. And I think the next one is, I think, very similar in spirit. So if you look at SX and SY, right? Given that, okay, so how would you saturate SX and SY if you had to, right? You could push 1 unit of flow out there with this P plus 1 incoming units of flow. You could steal 1 unit of flow here and push P units of flow down here. And you anyway have P plus 1 units of flow coming in here. So you can send P plus, right, so let me see, 2P plus 1 unit of flow here, and this should be okay. So what we want is 2P plus 1 should be at most P plus Q plus 1, but that's okay because Q is strictly greater than P. Okay, so that works out. Does that add up? The fact that there is a flow saturating both of these edges, you can actually do this. And this is the best you can hope for, actually, because this is like from the S side, this is a bottleneck, you know, that the flow landing at, going out of S and landing at T, they both have to be equal. So you cannot push any more flow more than this, because this is really a min cut in that sense, right? So that also implies that you cannot saturate, you cannot saturate both XT and YT, because that would be too expensive to do, right? Because that is going to be, I think, greater than what we can afford from the S side. Okay. So because there is a flow that saturates both SX and SY, the second option is not true, which says that there is no flow that saturates both of these edges. Here is a flow that saturates both of these edges. On the other hand, because, you know, the capacity of the edges, if you look at the total capacity of the edges incident on T, it is 1 plus 1 plus P plus Q. And Q is strictly greater than P. So this is strictly greater than 2P plus 2. 2P plus 2 is the total capacity of the edges incident on S. So you know that all the flow you push out of S must eventually land at T. So if you manage to get a flow which saturates both the edges incident on T, then that means that you should have been able to put that amount of flow from S as well, but that will violate the capacity constraints on the edges of S. So you will not be able to you will not be able to saturate both of these edges. So because that option is true, the other statement, the statement which says there is a flow saturating both of these edges, that statement is false, and that's why that's not correct, right? So we are given that Q is greater than P, and B is, I think, bigger than the largest positive number. That's yeah, first choose a number bigger than the maximum positive value. And here we have chosen B to be P plus 1. Yeah. So if B is P plus 1, it doesn't mean that P is greater than, P is greater than Q. You're given that Q is greater than P, and that's the case that you want to analyze. Yeah. And I mean, I believe the next like the 10th question is like a very similar combination of like arguments, like in a very similar spirit. Yeah. So do you think, would it be fair if I left that to you as like an exercise to double check? Cool. All right. Okay, great. Yeah, I hope that's not out of frustration. Yeah, I mean, I think it's just like the opposite. Okay, great. Yeah, it's yeah, I think it's the opposite inequality with a similar implication, and yeah, I think that's doable in a very similar way. So yeah, okay. So I hope that made sense, and cool. So I think. Yeah, so we've gone over a bunch of the assignments here. So notice that although we did discuss the week 12 assignment, you should not expect questions like the week 12 assignment to come in with actual numbers for large cases. As I said, if you see a large number, it means there's a pattern. You expected to find the pattern and solve it. You would not be expected to do anything that involves writing code. On the other hand, you might still get questions in that spirit where you're asked to verify which of the following recurrences will work. Okay, so we may give you a problem or a setting like that, and we will propose a recurrence and we'll ask you if you think it's correct, or we'll propose a bunch of recurrences. You may have to look at it. So that happened a lot in the week 11 assignment, right? So expect questions more in that format for the DP topic. So I noticed someone somewhere was asking how many questions there are. I honestly don't remember. I do know that they add up to 100 marks, and most questions have like a weightage of 2 or 3 marks. But beyond that, I don't, to be honest, I don't really remember. What I do remember is that in the second part, there are like this, I think either 2 or 3 questions, something like that. And each of them have a lot of subparts. So just, as I said, don't look at the question and say that, oh, this is too much to read. Okay, just read it. And, there are at least a few subparts there, which are kind of just working out examples. So it should not be too difficult. Okay, so if nothing else, you should get some value out of that. Now, about whether there's negative marking or not, I actually don't know, to be sure. I have not asked for negative marking, but just check the scheme, just check what the rules say. Okay, there are lots of instructions in the beginning. So I don't know if you're writing an NPTEL exam for the first time, then please make sure to read the instructions carefully. Okay. So it looks like most of you have an exam on Sunday. And as I said, my most important piece of advice pre-exam would be to make sure you are well rested and relaxed. And as I said, think of it as going into a programming contest, which, given that you're doing this course by now, you must have done quite a few of them. So the idea is that it's a mix of the kind of assignment problems you've already seen, and it should feel like a pen and paper version of or a non-coding version of a programming contest. That's what it should feel like. So try to go in with that sort of a mindset. Yeah. Okay. So, I mean, I think hopefully this was useful last minute preparation. And, as I said, a couple of assignment questions have been corrected. I'll post the corrections on Discord. If I missed anything, so somehow I don't think I am either very bad at dealing with Discord notifications. It's possible that I may have missed something. If there's anything last minute you want to clarify, please post it on Discord and I'll take a look. Okay. So thanks so much for sticking around until so late. I'm sure it's dinner time, time to get some rest. So yeah, thank you. That's so sweet of you. Thank you so much. Yeah, the courses are finally done. I'm looking forward to uploading some extra videos and some, maybe more random segmentary type content on YouTube. If I do that, I'll let you guys know. We'll keep the Discord community going, so it's not really goodbye, but from the point of view of this course, this particular edition, thanks a lot for sticking around, and it's been a really motivating experience working with all of you. So really appreciate all of the, all of the interactions, and you all have been such a support. So thanks a bunch. And as I said, make sure you take care and get good rest before the exam. Good luck, and, we'll be in touch right after as well. Okay, so take care and let me know how it went once it's done. Okay. All right, so good night for now then. Maybe we should call it a day here. If there's something you forgot to ask, just ask it on Discord, and make sure to ping me so that I will definitely check it out. I'll be on high alert tomorrow. If there's anything that comes up, I'll try to resolve it. Yeah, cool. All right, thanks all of you. Good night then, Raviraj, Krishi, BFS, DFS, and DFS, BFS, all the rest of you who are here. Thank you so much. Good night. Bye-bye. Thank you.